All right, this is the start of Unit 2, which is going to be on gases, and we will learn a few new things, but I do want to go over some of the gas laws and some of the unit conversion stuff that we did in Chem 1 that I'm going to expect that you remember. So I wanted to quickly go through that. And again, this is all in Chapter 10 of your book. So if you need to review any of those items, feel free to do that. All right, so first of all, when we talk about gases, we talk about pressure, and pressure is the force exerted by gas on their surroundings. So it's the force exerted by a gas on their surroundings, or more specifically on the walls of the container that they're a part of. Now, it doesn't have to be gases, but when we think about pressure, we usually associate it with gases, and that's what we'll be doing, obviously, in this unit. So the force exerted, and if it exerts more force or more frequent force, then it's going to have a greater pressure, and less force means a lower pressure. A barometer is the device that we use to measure atmospheric pressure, and the very first one was a glass tube with liquid mercury that was inverted into the disc that had mercury. There's a picture on the next slide. And as the pressure rose, the amount of mercury rose in the tube, and that's how the pressure was measured. And we use barometers now in order to measure outside weather conditions. And more specifically, if you have a storm is coming, you're going to get low pressure. And if you have, it also changes when you have altitude. Right, so this is a picture of what that first barometer looks like. And so inside this tube or this container is mercury. And as the temperature rose, the amount of mercury rose in the tube. And that's where the unit millimeters of mercury came from, because they actually were measuring the millimeters of mercury in the tube. A manometer is an instrument that's used to measure the pressure within a container. And so anytime that we're talking about pressure inside of some sort of container, whether it be with a piston or something like that, a manometer is going to be used in order to find its pressure. There are a bunch of different units that we use to measure pressure, and this slide talks about some of the most common ones. And so millimeters of mercury and torr are two of them. Those two units are the same. They're equivalent to one another. All right, so some of the other units that we will use to measure pressure are atmospheres, which is the same as ATM, torr millimeters of mercury, I just mentioned, and then pascals is another one. The SI unit for pressure is actually a pascal. Because this is such a large number, we often measure it in kilopascals, and so this would be 101.325 kilopascals. Now, many of these pressure units are on your reference sheet. In fact, atmospheres, millimeters of mercury, and torr are on your reference sheet, but kPa and pascals are not. So these two are things that you are going to need to memorize for your test and for the AP exam. But the other ones, atmospheres, millimeters of mercury, and torr, are given to you on your reference sheet. And so you will need to know how to convert between those units. And my recommendation is just to set up a proportion similar to what we were doing in stoichiometry. So for example, if I am asking you to convert 7.6, let's just say atmospheres into let's say how many kPa that is. And so I would do 7.6 atmospheres is equal to X kPa. And then on the bottom of my proportion, I would set up your standard units. And so atmospheres, I would put 1 ATM on the bottom, and kPa, I would put 101.325 kPa on the bottom. And let me grab a calculator. And I would do 7.6 times 101.325, and then, of course, divide by 1. And you would get that that's about 770 kPa. And you can use that that method for any of the unit conversions. And again, remember atmospheres, millimeters of mercury, and torr are all on your reference sheet, so they're not something you need to memorize. That's something you will get on all of your tests in class, and you will also get on the AP exam in May. The kPa and the pascals unit are not on your reference sheet, and they are used, so I would recommend that you put that on your list of things that you need to memorize. One additional thing I do want to mention that's related to pressure units and this slide is the term STP. So STP stands for standard temperature and pressure. And a lot of times you'll be reading a question and it will talk about a certain amount of grams of gas in a balloon at STP. And so you will need to know what that stands for. Now, those conditions are on your reference sheet, but you just need to know what it means when it says STP. And so STPs, those standard temperatures and pressures, are 0 degrees Celsius and 1 atmosphere. And because 1 atmosphere is equal to any of these down here, so you could also say that STP is 760 millimeters of mercury, or you could say that STP is 101,325 pascals. Any of those will work. The two things at the bottom are not things that we will use very often. Force and newtons are things that are used in physics, but this is just showing you a relationship between what we're doing in chemistry to something that you may see in physics. And so pressure is force divided by area, and the units for force are newtons, and area is often measured in meters squared. And so a pascal is also equal to a newton per square meters. Again, not a unit that, or not a equation that really you're ever going to see in chemistry, but it's just a way to help you draw some connections between some things that they do in physics to what we're doing here. All right, and then the last thing that I want to talk about in this video are the gas laws that you learned in Chem 1. So in Chem 1, we talked about Boyle's law, Charles' law, Avogadro's law, and you may have talked about the combined gas law as well. So I'm going to quickly review those and give you the combined gas law, which is the one really that you need to memorize. And so the first one looks at Boyle's law, and Boyle's law says that when you take the pressure of a gas and you multiply it by its volume, you're always going to get a constant. And because of this relationship, you can say that the pressure of a gas and the volume are inversely related. So what that means is as one goes up, the other one goes down. This only really holds true at low pressures. And as the pressures go up, there's going to be a little bit of variance, but not too much. And again, the deviations are very slight at 1 atmosphere. And so we assume that those variations don't really exist. And so because you can take the pressure of something times its volume and you get a constant, well, I can take the pressure and the volume of some other gas and get a constant. Well, a constant and a constant are equal to one another. And so that's where the traditional equation for Boyle's law comes in, which says the pressure 1 times the volume 1 is equal to the pressure 2 volume 2. And so if we're dealing with some sort of change in pressure and volume, you can use this. Now, this assumes that the temperature and the pressure are held constant. It assumes that the temperature and moles of the gas are constant. And so that is Boyle's law. And here's a picture of Boyle's law. So you can see as the pressure changes inside the container, the volume is going to change, whether it goes up or down. They're inversely related. And here's another picture. The next gas law that you should remember from Chem 1 is Charles' law. And Jacques Charles is the scientist that came up with it. And basically, he came up with it after taking the very first solo balloon flight. So he filled the balloon with hydrogen gas and realized that as you increase the temperature inside the balloon, the volume also increases. And so we say that according to Charles' law, that there is a linear relationship between volume and temperature, or another way of saying that is they are directly proportional. So as one goes up, the other one goes up. And it's really important to remember that when you're dealing with this, that your temperatures must be in Kelvin. And the reason for that is because the absolute zero. So absolute zero is when you have 0 Kelvin, which says that there's absolutely no particle motion. It's never actually been reached, and as you can see here, they've gotten pretty close, but they haven't ever reached that exact absolute zero. But if you look at the traditional version of Charles' law that we all know, V1 over T1 is equal to V2 over T2. And if I decide not to convert the temperature units to Kelvin, if I leave them in Celsius, so let's just say I have a balloon that is 6 liters and the volume or the temperature of the balloon is -2 degrees Celsius, and I want to know what the volume would be if I raised the balloon temperature to 4 degrees. Now, if you do this math, you're going to get a negative volume, which is not something that is allowed. It doesn't make any sense. And so in order to fix that problem, you need to have your temperatures on an absolute scale. So we would put that the volume of the balloon is 6 and the temperature of the balloon would be 271 Kelvin. And the volume of the new balloon is what we're trying to find, and the temperature of the new balloon would then be 277 Kelvin. And in doing this, we can make sure that we get a positive volume, which is what we want to have. Next law is Avogadro's law. So Avogadro's law says equal volumes of gases at the same temperature and pressure contain the same number of gas particles. And so this looks at volume and temperature, volume and moles, and it says that they are directly proportional. And so if you take this equation here, the V is equal to A times N, and A is just it's another constant. I can rearrange it and say that that constant is equal to V over N, and then it works just like the other two laws. And so V1 over N1 is equal to V2 over N2, and you can figure out solve for either any of those options, V1 or N1. And remember that when chemistry, when you see N, N is the number of moles. I'm going to do an example. All right, I'm going to do an example using Avogadro's law because it's not a law that we used very often in Chem 1, especially if you had me for Chem 1. So I just want to make sure that you understand how to use it. So the question says, suppose we have a 12.2 liter sample containing a half a mole of oxygen gas at a pressure of 1 atmosphere and a temperature of 25 degrees. If all of the oxygen is converted to ozone, which is O3, at the same temperature and pressure, what volume of O3 would we have? And so if I look at this and say my temperature and my pressure are the same and all I have are volume and moles, I know I can use Avogadro's law. So V1 over N1 is equal to V2 over N2. So if I just look at this question and start plugging in the numbers that I have, so my V1 is 12.2 liters of O2, and it says I have a half of mole of O2, and I know that I'm trying to find the amount of liters of O3. Now, I need moles of O3 on the bottom, which is something that I don't have. Well, if these two are equivalent, so I need to figure out if I have a half a mole of oxygen, how many moles of O3 is that equal to? And I can figure that out by just using stoichiometry. So if I have a half a mole of O2, and I'm trying to find X moles of O3. Now using stoichiometry, if you have moles on the bottom, you can use 1 mole on the bottom times oxygen gases coefficient. And same thing over here, if I have moles on the top, I can put 1 mole on the bottom and times ozone's coefficient, which is 2. And let me just clean this up a bit. Okay, and do your cross multiplication, and you get 0.33 moles of ozone. And so according to this balanced equation, if we have a half a mole of oxygen gas, that's about a third of a mole of ozone. And so this third of a mole of ozone can go down here in our Avogadro's law expression. And now we can use Avogadro's law to figure out just how many liters of ozone gas we have. And so if I do the math, you're going to get 8.1 liters of O3. Looking at 6 figs, 0.50 has 2. So my answer has 2. And so here is the final answer to this question. And that concludes the individual gas laws that you need to know for AP. And in the next video, I'm going to talk about the ideal gas law, the combined gas law, and gas stoichiometry.